So let me continue our discussion that is on version space that we discussed in the previous class. That uh, we have discussed about two algorithms. One is findes, which finds the maximal specific hypothesis, and then we discussed about list all elements kind of algorithms, where all the hypotheses in the version space, one by one in the hypothesis space, we check, and if you find that it is consistent, so consistent with respect to training examples, so then you include it in your result set. So set of all consistent hypotheses is what is your version space. One example is here. So just can you tell me that what is meant by this consistent hypothesis that we discussed? Can one of you just explain what is a
So-
consistent hypothesis?
Something that satisfies all the training examples.
Which means that
All the positive training
yeah,
examples.
all the positive training examples it should satisfy. Again, no, for all the negative training
Actually,
examples also it should give 0, right? For all positive examples it should give 1, and for all negative examples it should give 0. Okay. Rest of the data point which are not included in your training examples, it may give any other arbitrary result, but minimally it has to satisfy that, and that hypothesis is called a consistent hypothesis. So naturally, a consistent hypothesis is not also unique, and a version space is the set of all such consistent hypotheses. It's a subset of hypothesis space that you understand. Now, one of the ways that you can represent this version space in a more compact form, because we have discussed that in this particular case, particular example, we have a certain order in the hypothesis space. That means you have the relationships of a more general hypothesis than the other one. So there is a relationship between two hypotheses. One could be more general than the other one. But no, it's a partial relationship. That means they may not be related also. But there exists a relation, so it is something like this. So it forms a lattice structure. Can you tell me once again that suppose I have two hypotheses, say H1 and H2, and when do we say H1 is more general than H2? Can you tell me?
so for all x, if h2 of x equal to 1, then that would imply h1 of x is also equal to 1. Then we would say that h1 of x is going to be more general than h2.
Very good. Right. So that is what that means. In H1, whatever data points are satisfied by H2, that at least they should be satisfied. It can satisfy in more number of data points also. So that is the concept of the general more general relation, and that relation creates a kind of a lattice structure in the hypothesis space. And when you consider a version space, so in the lattice structure you will have there are two particular set that you can get. One is a set of all hypotheses which are I should say the that is called the most general set of hypotheses, most general hypothesis, and the other that is here it has been shown by this G. Let me use once again a pen just to highlight. See, this is the most general set of hypotheses. So we call it G, and this is the most specific set of hypotheses. That means all the hypotheses in this set, they should cover, minimally they should, or maximally they should cover all positive examples of the training data set. So there should not be any other additional, at least maximally in the sense that that is a if there is any specific hypothesis, that means if you have there exists any hypothesis which is less general than this, or I should say the more specific than this. So if I say more general, the other relation I can say more specific. So if there exists any hypothesis which is more general than this, then it will exclude one of the positive example. So I think there was somebody has pointed out these things in my previous class. I mentioned that it will only satisfy all the positive examples. Now that is not really correct in the sense that there could be some more data points which could be satisfied, but when we say it is most specific means there does not exist any more specific hypothesis with respect to this hypothesis which will cover all the positive examples. So that is the definition, more tight definition in that sense. So in this case, as you can see that this relationship Sunny worm, this hypothesis Sunny worm and then question mark, then strong question mark. I hope that you understand what is meant by this time, because each position denotes certain attributes, and this shows that which value will be required to satisfy that hypothesis. It's an AND logic, so all of them should be satisfied. So in this position, the value has to be only Sunny. If there is any other value, then it is not satisfied. Here the value has to be worm, and otherwise it is not satisfied. But in this position, the value could be any other. This pane is also visible. I mean, if I don't draw, is the pane is visible to your end?
No, sir.
Okay. So only when I mark with the red color, then only it is seen.
Yes.
Fine.
Yes, sir.
Okay. So in the training examples, what we had, I mean, if you remember, there are 4 sets of training data points we have given. 3 of them were positive and 1 of them was negative example. So it is maximally, it is satisfying. This hypothesis is the maximal specific. So it is maximally satisfying at least those 3, and maybe another another data point also it can satisfy. But you cannot get any specific hypothesis, more specific hypothesis from this which will satisfy all these 3 examples. So that is the understanding. Whereas if I consider the most general boundary, so in this most general boundary, you can see that here you are covering not only positive examples. Actually, we are more concerned about here negative examples. So what I said that in this case, this hypothesis should be consistent. So all the hypotheses, say all these hypotheses are consistent. Say this hypothesis. So every every set of Boolean literals that is shown as a vector by using this two brackets. So they represent a hypothesis. So these are all hypotheses. And why they are put here? Because they are in a partial ordered sense. You cannot say this hypothesis is more general than this one, right? Similarly, so that's why they are put into the same. But they are also most general hypotheses, because all the training examples what has been given, they are satisfied. Positive examples will give an output 1, and negative examples will give an output 0, right? So you can see here, for example, yeah.
So I have a question. If I take a hypothesis more general than G, then it will wrongly satisfy our negative examples. Am I correct?
No, that is not. That is the constraint. So you cannot say any more general. It is not going to satisfy any negative example. It has to be consistent. You give some example here.
No, if I take a hypothesis more general than G.
Yeah. Then for example, all question mark. It is more general.
Yes, sir. It will wrongly satisfy the negative example.
So that's why it is not included in your version space.
Okay, sir.
And that is how these boundaries are. So this is a boundary. If you get more general hypothesis from this set, that would wrongly satisfy one of the negative examples, at least some negative examples, at least one negative example, right? So
Okay, sir.
this is the compact representation in the sense, if I specify this G and S, that is sufficient, because in a lattice structure, as you know, that since they are all ordered, so by giving these two sets, I can compute all the intermediate hypotheses which are more general than S, but less general or more specific than G, right? So in this way, you can get the version space. So there exists an algorithm which will compute these two boundaries. It need not enumerate all possible hypotheses, that what we did in the previous exhaustive algorithm, which is naturally quite inefficient, that we have considered every possible hypothesis and then check whether it is consistent or not. But it is not required. What we need to do, that from the training examples, by looking at the positive examples, we should get this maximal specific boundary from them, and by looking at the negative example, and also now you have to look at S also while doing the negative, because you have to satisfy the positive examples. You have to also consider that it should not satisfy any negative example also. So that means some hypothesis where if you get a negative example, it has an effect on S also. Some of the hypothesis needs to be modified, but mostly we look at positive examples and try to cover them. And if there is a negative example which gets satisfied, then no, we remove them. So that is what we do. Similarly, let me explain that algorithm. We'll discuss that part. Okay.
Sir, I have a question.
Yeah, please.
Sir, I have a question that the most specific hypothesis should not satisfy the negative examples from the training set, no?
Not only that, it is not only most specific. It is any hypothesis in the version space should not satisfy any training example, any negative training example.
So we are finding this most specific one through this find S algorithm. And
no. That is the find S algorithm will not give you this boundary. So there is a change. So I will discuss. Find S is not going to give you S. Okay,
sir, but
that is maximal. Find S give you maximal specific algorithm, maximal specific S. So it is in the sense find S considers that all negative examples are if there is any negative, all positive examples, whatever hypothesis it satisfies, or whatever positive examples are there, other than that, every hypothesis is negative, every data point it is negative, but to make it maximal specific, some of the data point may get positive. But if there is a contradiction, then actually the find S has this limitation. We mentioned that it cannot determine from the training example whether there exists any contradiction or not. We mentioned that.
Sir,
okay?
if like the first argument, the first argument means Sunny have 3 arguments. So while we are searching, if the first one is this Sunny worm question mark strong question mark, and if we find another positive example from the training set which does not include this Sunny, like these have 3 arguments, no? So it does not include the Sunny, that is cloudy, rainy, and then we will make it question mark.
Yeah, that's true. That's right.
So, but if there is another training set in the training, another example in the this training set which includes the third argument, and it is negative, then unfortunately we make this the first argument question mark. So this will also make the this negative training set to be also satisfied.
Actually, find S does not look at negative example, and it assumes that your target function exists, right? So that is the limitation in find S. If since it does not look at negative example, if there is any inconsistency in your data set, then it will not really going to give it. I mean, it is not going to detect that part. Okay, so let me
Sir, one
proceed.
more thing.
Yeah.
So in the set G, 3 question marks strong, 2 question marks. Should not that hypothesis be in G also?
Which one?
3 question marks strong, 2 question marks.
No, we'll come to that. So you are saying 3 question marks, strong 2 question mark, but 3 question mark means now that means you are saying that even the cloudy also could satisfy, na?
Sir, in
Suppose
this,
it is this sunny becomes. I mean, you are saying
using the first and third middle hypothesis.
Let me put. So you are saying this if I make it question mark, na? That's what you are saying.
I am adding one more hypothesis to G, that is 3 question marks strong and 2 question mark.
No. See, that is a different thing. So that you are doing it.
That should be there, na? Because using the first and second intermediate hypothesis, we get the first one of G. Using the second and third, we get the second one of G. So using the first and third intermediate, cannot we get one more, which I am suggesting?
First and third, you are saying this one, these two.
No, in the intermediate 3 hypothesis, first and third.
These two.
Using those two, there should be one more hypothesis in G, right?
Using these two, there would be one more. See, in the G, that means they should be more general than G. In the lattice structure, they should be more general than G.
Not exactly. All the hypotheses in the G, they are not related to each other, right? By the ordering relation.
Yeah. So that's what I mean. These two, if you are saying these two, if you want to get more general hypothesis for these two, so that should be also. So which one hypothesis? Give one example then.
Yes, sir. As using the first 2 intermediate, we get the sunny and 5 question mark. So similarly, using the first and third, I would get 3 question mark and strong and 2 question mark.
Yeah, 3 question mark, strong,
and then 2 question marks.
And 2 question mark, right?
Yes, sir.
Yeah. So that you are getting. That you would like to say that this should be put here.
Also in the G.
When it is G. But in that case, you can see that in the hypothesis, so there would be some negative examples, which will not be satisfied by this. So there is, data set. See, it depends upon your data set, right? Suppose there is a data set which takes, say, cloudy at this point, okay, which takes cloudy, warm, and whatever this value, and then strong and the other 2 values. Now, if that is a negative example, then you cannot put it here.
So if that would be negative example, then the third intermediate hypothesis would not be satisfied also, right? Because the third intermediate hypothesis shows that question mark in the first place.
Yeah, but no, the question is that there is a worm. Suppose there is a negative example, instead of worm, there is something else.
Sir, there is strong in the specific one also, no? So if you take the specific and all other question mark, then it should also satisfy because the specific one has strong in it.
Yeah, the specific one has strong and specific one also has sunny, right? So if you take anything cloudy, so what actually is shows that it has to be consistent. It has to be consistent with respect to your training examples. Now, if you have anything cloudy in this position, because no, you are telling that anything cloudy also would be satisfied here. Okay, so there you will get a problem because you have this. You will in your training example there is. It depends upon your training example. So hypothetically, you cannot just put, but just by looking at the version space. That is my point. This version space has been formed by looking at the training examples. Now, it depends upon if there are training examples which contradicts this, then it cannot exist. That is the point.
Sir, there was a training example actually.
So let me. So that's what I'm saying. So let me continue. Go to the training example. So just by looking at the structure, you cannot say, sir, you can make more general of these two and include it. you do not know what was in the training example. Okay, so if the training example, your negative examples are not there, they could be included, but probably there are negative examples which should put these restrictions. Okay, so let us proceed and let us see that what are those examples and why actually this is the minimal this is the version space of those set of examples. So this is this is most compact representation in that sense, as I mentioned, that you are storing the most and least general boundaries of space, and here you are generalizing the most specific boundaries and you are specializing the most general boundaries. So that is the task. You are using positive samples for that while generalizing most specific boundaries, and while specializing most general boundaries you are using negative samples. And but no, you have to observe again both the sets while while checking positive samples you need to also check whether there is any contradiction in your general boundaries, in the hypothesis set of your general boundaries. If there is any contradiction, that means this sample is not accepted, then you have to modify it. Similarly, if there is any negative example, then also you have to see whether there is any contradictions, so to make it consistent. And then now if I get these two, then from there we can generate all intermediate edges in the version space, and any edge in version space must be consistent with all training examples. So this is what the general boundary G, the set of its maximally general members consistent with D. So summarizes the negative examples, and anything more general covers wrongly a negative training example. That is the idea. Similarly, the specific boundary is the set of its maximally specific members consistent with D, and it summarizes the positive examples, and anything more specific fails to cover a positive training example. So I will be giving you with examples this particular thing. So there is a theorem which says that this version space will give you rather it just mentions that it's a kind of the definition of version space, that it is set of all consistent hypotheses. And this theorem says that this lattice structure, this if you have these two boundaries, general and specific boundaries, then any hypothesis which is more general than an hypothesis of than one of the hypotheses of this specific boundary, and which is less general than one of the hypotheses of general boundary, then that hypothesis should be consistent, and that is a member of version space. Okay, and that is the one and only possibilities. I mean, it includes all possible consistent. This property is true for every consistent hypothesis. So this theorem says that means if every H satisfying RHS is in version in the VSHD, and every member of version space should also satisfy this property. So these are the two things you need to prove. So let us go through a bit the logic about the argument of this proof. So this is the statement, and as I mentioned that you have to show that every H satisfying RHS, that means what is the right hand side condition says that H is more general than a hypothesis in the specific boundary, most specific boundary, and less general than a hypothesis in the most general boundary. So if that is what H character, then H should be a consistent hypothesis. That means it should be in the version space. And the other thing says that it's all inclusive. That means any member of version space should have this property, right? So argument is quite simple in the sense that consider there exists such G and S two hypotheses in these sets, capital G and S, and H is a any hypothesis in the hypothesis space, and you have these relationships. That means we are considering the first statement. I mean, first fact we are trying to prove it. So we have to prove that H is consistent. So naturally, if H is more general S, so H satisfied all positive training examples, right? And since G is more general H, G should satisfy all positive by H, and H should not satisfy any other examples. That means all negative examples should be also, no, should not be satisfied by H. That is what. It cannot satisfy any negative training examples also. So that is how now H is a consistent hypothesis. That is the argument. And the second one is that now since H satisfies all positive training examples and no negative training examples, and no H is then H has to be, this is the property, H has to be then more general than S, whereas G has to be more general than H, right? So this is the proof of that. If in a version space, if you have these two boundaries, then you can get all other hypotheses which has this particular ordering. Now let us discuss this algorithm, candidate elimination algorithm, where we will be computing these two boundaries, and that would clear some of the doubts what you were mentioning. I mean, you are that I mentioned that by looking at the version space, you cannot say that no, what should be included also another, because that is the result. That means this version space is all the hypothesis in the version space is consistent with the training examples, and there should not be any other hypothesis in the hypothesis space which will be consistent. Now, so how do you ensure that? Let us see this particular algorithms. So we will start with these two set. Like we will include the maximally general hypothesis in H, and we know that what is this hypothesis? Maximally general hypothesis, initialization. It should be all question mark.
All question.
Right. Similarly, maximally specific hypothesis in H, which means all null, right? So these are the initialization. Then for each training example, if it is a positive example, what should you do? You should summarize the S. That means the most specific boundaries. You should look at those hypotheses. So what you need to do, you remove from G every hypothesis inconsistent with D. So this is what I told you, that no, for every positive examples and every negative examples, you need to look at both the boundaries. Though mostly you'll be concentrating your operations in one of those boundaries, positive examples should be covered by these maximal specific hypothesis sets, and negative examples, should make the general boundary more specific, so that it should exclude those negative examples which were earlier satisfied. So that is what G has to be modified. Anyway, so let us see that remove from G every hypothesis inconsistent with D. Now, for each hypothesis S in capital S, you find that if it is inconsistent with D, which means that this hypothesis is not satisfying D, because it's a positive example, then you have to make it more general. So that kind of modification, but what this task is described in this fashion. You should remove this hypothesis and take the hypothesis which will have the minimal generalization of H of S, such that H is consistent with D. It is something like that same step of find S algorithm, where given a hypothesis, given a positive example, you are trying to get maximal specific next hypothesis, but you are doing it for all hypotheses in S. You are doing the same thing, and you should check some also see that some member of G is more general than H. Now that is also one of the thing you need to consider here, and then you remove from S every hypothesis that is more general than another hypothesis in S. So while doing this thing, actually you are also observing that that it should not include any it should be consistent with the hypothesis set of G. That is what you are observing. That means there should be because G is a general boundary, so it excludes all the negative examples. Now you have to ensure that that at least there is a hypothesis which is more general than this modified H in G, and remove from S every hypothesis that is more general than another hypothesis S. Now these are all some specific cases with examples only one can understand. So maybe all these steps are not required in every time. because you will find always that no hypothesis, whatever you are getting, there is no such condition exist. But if such condition exists, that some hypothesis, because of this operation, because you are choosing the most specific hypothesis, and somehow if you find something was more general, then that has to be removed. Now, if D is a negative example, then remove from S every hypothesis inconsistent with D. Once again, you see that this is the effect of negative. Earlier in the find S algorithm, you are not doing these things, but here you are taking these things. So if you get a negative example, there is an effect. So if you find some hypothesis which is inconsistent with D, then you have to remove, and you consider that no, I think that removal should be fine. That is what. And for each hypothesis G in G that is inconsistent with D, which means that these negative examples are satisfied also there. So now G has to be made more specific. Now G has to, so remove G and add G to all minimal specializations H of G such that H is consistent with D and some member of S is more specific than H. So actually it says that it is not only one hypothesis, you have to add multiple hypotheses which will be the minimal specializations of the present hypothesis small g, because that is not consistent, because with respect to this negative example, this small g hypothesis is not consistent. Then remove from G every hypothesis that is less general than another hypothesis in G, because you are always trying to keep the most general boundaries. So any less general should be removed. And essentially, what you are using positive examples to generalize S and negative examples to specialize G. One of the interesting fact is that it is independent of order of training examples. So in any order, this negative and positive example may come, and you have to modify your general boundary and specific boundaries, most general and most specific boundaries, and that would always retain the status. I mean, whatever training examples you have visited so far, it will reflect a version space consistent with respect to that set of training examples only. So that is one of the properties of this algorithm. So the convergence is guaranteed. That means if there are no errors, I mean that is the assumption, and if there is H in the hypothesis describing C, that means if there is any target concept. Actually, the problem is that if there is no target concept, then you will get an empty set. You will get an empty set in that case.
Sir,
yeah.
Sir, in this algorithm, we are only maintaining the G and S. That is the means most general and most specific set.
That's right. That's right. I mean, because I told you that is sufficient to get all other hypotheses which are consistent in your lattice structure. Okay. So let me go through these example sets once again. I think that would make some of the doubts, more that would clear some of your doubts. Say you have this is the initial set of boundaries S and G. I told you that S naught is all null all null literals. So that is the most specific hypothesis, and most general is all question mark. Now you get a training example. See, this is the first training example that you get after this, and which is a positive example. So what you should do in this case, you need to make it maximally specific with respect to this, right? Because you will find this is contradicting, this is not accepting. So you find this is accepted by G naught. So you are not doing anything there. But you find this is not accepted by this one. So what you do, remove from G every hypothesis inconsistent with D. So that is not required. This is a step, remove from G. Then for each hypothesis S in S, which is the only hypothesis here, let me use my pen. Yeah. So you see that for each hypothesis S in S, which means only this hypothesis. Remove S from S, so you have to remove this hypothesis from from your from the set S, and then add to S all minimal generalization of H of S that are specializations of a hypothesis in G. So that also there are specializations. So since it is all question marks, so any hypothesis is a specialization of G naught. Now in this case, only hypothesis that can be included is this one only. That you agree is that only hypothesis that can be included only this one, right? So this becomes your S1 now, and remove from S every hypothesis that is more. So it is not, this question is not coming here in this case. Okay. So that's why your S1 becomes this and your G1 becomes this. Okay, this step is simple to understand. So next, let us consider the next iteration. We will consider the next training example. Now this is also a positive training example, and as you can see that this this example is not satisfied by the hypothesis presently what is there in S1. It is satisfied by the G1, but it is not satisfied by the hypothesis of S1. And since it's positive also, you need to modify it. So your S2 has to be the maximal general. So that just a generalization which will cover this positive example, minimal generalization of a hypothesis of S1 which will cover this example, that you need to consider in S2. So we have already discussed. So it should be sunny, warm, question mark, strong, warm, same. And G2 means general boundaries in this iteration. So these subscripts are all, they are shown by the iteration number. So G2 is the general boundary in the second iteration. So you see that it remains the same. Now you will get a negative example. So here you can see that what is the negative example? You are saying rainy, cold, high, strong, warm, change. Now you can see in S2, actually this example is not satisfied by the hypothesis in S2. So naturally, you did not do anything. I mean, you are not going to remove that hypothesis because it is inconsistent with D. It is not inconsistent. It is consistent with this training example. But the hypothesis in G2, all question mark, that is inconsistent because this is not going to be satisfied, and that hypothesis takes it. So what is the least generalization or sorry, least specialization of this this hypothesis, so that this hypothesis would be excluded. But once again, you should see that that hypothesis should also be a generalization of all the hypotheses of S2. So that is a constraint. So when you are doing it, suppose a generalization could have been that as you can see with respect to GT, what are the generalization could have been there? I mean, if I don't consider because S2 gives you set of all positive examples. Now that is how G2 needs to be modified. It should satisfy them also, those positive examples also. So you should not generalize in such a way that some of them becomes negative, right? So so in this case, what are the generalization are possible? Can you tell me?
One can be sunny, then all question marks.
Sunny, all
That
question mark. Yeah.
So change one parameter. Just flip one parameter.
Sunny, warm, all 4 question marks then.
Sunny, warm, all 4 question mark. But sunny, all question mark also will be more general. That is the least general part. That would take care of sunny, warm, all question mark also.
Sir, 5 question mark and 1 attribute. For example, as sunny question marks, then question mark 1, all question marks.
Then,
and
what about high? Do you require to do anything there?
No.
That is not. You do not require to do anything there. What about strong?
Sir, negate one attribute and make all other question mark.
So you are saying if I make strong, all question mark and strong. That's what you are saying? If I put all question mark and strong, that no, you are saying negate one attribute.
Yes, sir.
That means no, strong means weak. So all question mark weak, and will that be a consistent hypothesis? If you look at S2, S2 is a specific hypothesis, more specific hypothesis from that. Will it be a general hypothesis from the hypothesis set in S2?
Yes, sir. No, that will violate S2 also.
Yeah,
Right.
so that will violate. So actually, it is not. It cannot be there like that. Huh? So you have to check that part also. What about worm?
It can work.
So the worm and
Worm and all question marks.
worm and all question mark, right? So, I mean, it is a fifth position worm, no? Not the second position worm. Worm and all question mark. And what about the other one? Like same all question mark.
So 5 question mark and same.
That will.
5 question mark and same. Okay. So
Sir,
yeah.
worm and all question marks should satisfy the negative example.
Worm and all question mark will satisfy the negative. You are right. Worm and all question mark will satisfy the negative
I'm talking
example.
about second worm. Second worm. If we take second worm and all 5 question marks, then that will not satisfy this negative example.
Second worm and 5 question mark. Right. That is okay. I think that is fine. That is not satisfying. That is not going to satisfy this negative example, and that is also more general of S2, right? So we need to change it. So you see that these are the most specific. I mean, I should say most general, and this is the least specializations that you can do from G2. Any question? What would be S3? S3 will remain same. Is it clear now? Okay. Fine. So this is the state with respect to these three data points. Let us proceed. We have 4 data points. So this is the question: why are there no hypotheses left relating to cloudy and all question mark? So let us come to that. Why? If I give cloudy all question mark, if I put here, you can see that that is not a specialization of S2. Is it clear?
Yes.
Sorry, that is not a generalization of S2. S2 cannot be a general member of that. So it is inconsistent with S. Okay. That is what. So the following specialization is the third value, that all question mark normal is not more general than the specific boundary. If I put the normal, so I think normal in the third position, no? Yeah, third position. So it is not more general. So you are not putting them here. Already there is a question mark there. It's not more general than the specific boundary. So the specializations, this and are also inconsistent with this. I hope now you can find out that why actually some of you have asked questions now, why those two can be put together, and no, there could be more some more general. They could be general of those two, but no, with respect to your training examples, they are not consistent. So that's why it is not there in your boundary. So let us continue once again. So we have some more training examples. So this is the next positive example. which is sunny, warm, high, strong, cool, change, right? So since it is positive example, now what you see in the S3, this example is not satisfied, isn't it? It is not satisfied because warm becomes cool and warm. There it will be a problem. So you have to make it question mark there. I mean, you have to then make it more general, and then same and change also will have a problem. Okay. So there you need to put two question mark, but then the problem that you see that in G3, so this is the question. So this cool and change, it will contradict these two, and you need to generalize them. But if I generalize them, then this will have a problem. Is it clear? Then this will have a problem because then you have a hypothesis here which is not no specific to this one. So which means this needs to be also excluded. Right? You need to generalize it to question marks, like this is one question mark, and say you need to change them to this, and this needs to be no. This needs to be deleted. So you have this, like S4 is this, and you see that your G4 will be this one. So any question? So this is how you see that now every training examples will modify both these two boundaries. So though you have a positive example, it has also its effect on the general boundary. Any question? Okay, so let me proceed in that case. So why does this example remove a hypothesis from G? I explained that part, that no, because no, it cannot be specialized since would not cover new training examples. So you need to have cannot be generalized because more general would cover negative training examples and hence must drop this hypothesis. So this is your version space. Finally, you see that with respect to those four set of training data, this is the only set of hypotheses. Those are consistent. I hope now your questions related to those things, like just looking at the hypothesis, you cannot include something more general and something more specific. But you have to consider the set of training examples. So convergence of this algorithm, as I mentioned, that no, if there is no error and if there is an hypothesis in H describing the target function, then no, it will converge. And if there is no ambiguity, if there is no ambiguity in the specifications, then you will find both these two boundaries, they are collapse. They become the same, and that is only a single hypothesis in that case. And if you have seen enough training examples, you are expected to get your target functions in this fashion, right? For any false negative target training examples, algorithm will remove every H constant. So the problem is that if there is any error, then this consistency check will be also erroneous. So naturally, you may not get the corresponding correct target functions, and sometimes you may get empty version space because of the conflicts and contradictions. So you'll find that you will get empty version space. Another question which will be interesting to address, that is, as I mentioned, that actually it is not the order of the training example which matters here. Something matters, like depending upon the order, your computational efficiency your computation number of computations will vary. because number of possibilities, etc., will vary. Number of checks will vary. So, so the question is that is there any uh, any kind of policy of selecting an order of examples which will try to make this computation more efficient, right? So if you have that kind of flexibility, so you should choose this as that it reduces maximally the number of hypotheses in VS. That means when you are trying to get a version space, what you are doing, you are basically trying to narrow down your search space in your hypothesis space. If you remember that we started with the whole hypothesis space. That means S is null and G is all question mark. And then with each training examples, we are narrowing down this search space. And after narrowing down, whatever, finally, when you narrow down to that space which is sufficient enough to make all the training examples, all the hypotheses consistent with the training examples, that is what is your version space. So the question is that which training example can make this search faster, can reduce maximally the number of hypotheses in version space. So best training examples is, for example, if you can make your hypothesis space, reduce it by half, something like that. But no, it is difficult. It is difficult to determine that kind of preference, that kind of order here. Oh, I am almost at the end. So maybe
attendance sheet.
Right. So let me stop here here today. And just to summarize that, order of examples matters for intermediate sizes of SG, but not for the final, specific boundary and general boundary. So tomorrow we will continue this discussion. One of the thing I just let me mention here, since you have so many hypotheses, consistent hypotheses, now if you get a new case, you can use this kind of set of hypotheses. It's a kind of ensemble learning. So you have many possibilities, and for any new case, you try to see how many of them are satisfying, and accordingly you try to level them. We'll discuss, we'll elaborate these things. So let me take the attendance first. And then I will take some of your questions also at the end. Okay, I hope the attendance is downloaded. And so can you, is there any questions? I can take it for at least another 3 to 4 minutes or 5 minutes.
Sir, will the set S contain only one element? Is it guaranteed by this algorithm?
No. It is not that. It is not one element. It is a maximal specific. You see that in the algorithm it says that if you can have some hypothesis, alternative hypothesis also, which will be maximally which can cover all the positive examples. You can. So as I told you that unless you go with certain examples, it is difficult to comprehend. As if it seems that like find S algorithm gives you one particular hypothesis, and it looks like similar to find S, but it is not like find S, because what it is saying, you are removing an inconsistent hypothesis and then you are replacing them by maximal set of hypotheses. I mean, there could be a number of hypotheses which is consistent with respect to that data.
Thank you, sir.
Any question?
Sir, if it so happens that for a positive example, if it doesn't satisfy any of the conditions in G set, so like is it that it is a contradictory example that we have seen as far, or that can be possible?
Actually, it's difficult to understand what you are saying. That means you are saying that the example is positive and it is not satisfied by any of the conditions of G. Okay. Which means all were negative examples. That means you should it was saying that if it is inconsistent, then G needs to be that hypothesis needs to be removed from G, right? That is what is the algorithm says, isn't it?
But in that case, all of them will be removed, no?
Yeah, all of them will be removed. Yes, that's a contradiction. Yes.
Hello, sir.
Yeah.
So can you make the slides available on Moodle? Because I cannot find the concept learning slides.
No, you will not, because I told you it is at the end of my topic. You have to read the book, and also the videos are there. You can download it and go through them. Okay. Slides I will upload at the end.
Okay,
I cannot
thanks.
go on incrementally uploading the thing. Some of the things now I should mention here, because some of you are sending me individually mails about your exams, etc. I understand in these situations now we have difficulties, but we are all running through these constraints. You should understand that now you have become matured enough to handle different kinds of assignments at the same time. Just because you have an exam, don't expect that you will be only studying for your exam. So there is no considerations, because many of you are asking, give us consideration relaxation. I don't see it has to be there. You have to prepare your examinations. You have to do your assignment. You have to attend your classes. Only consideration is that if there is no examination at that slot, and no, if you find it is too near or it is just then you can drop out from the lecture session. Later on, you can go through my video lecture. But all your assignments, all the deadlines, you need to meet. There is no relaxation on that. And please try to have a book, as I mentioned. So tomorrow I will upload. Tomorrow, whatever may be my condition of this step, because now you have a quiz on Tuesday, so I will upload this slide set tomorrow.
Okay, sir. So the book name you said was Michelle, right?
Yeah. I mean, it is there. I think in the first slide that is uploaded. If you go through that slide, there is a slide on books. There, that you can find the name there.
Okay, sir. Thank you very much.
Okay.